Okay, folks, episode 102 of your favorite television series, we're going to look at areas and scale factors. What happens when we use a regular old scale factor and we apply it to an object? What does that do to the area of the image? Okay, so not a linear dimension anymore. Area is not linear. Section 8.4 of your textbook, Chapter 8, still in Unit 9. Here we go. A couple of the key things we want to look at. We want to talk about understanding the effect on area of the scaling, and we want to write a scale factor formula for areas. And then we're going to apply the square scale factor. Okay, let's see what all that means. Put it together here. Alrighty, so let's look at the creation of an image from an original or an actual here of a small rectangle that we're going to scale up this time. So it had a length and width of 2 and 5, and we scale it up by a scale factor of k equals 2. So the 2 becomes a 4 and the 5 becomes a 10. Sure. Okay, so if the original area, 2 by 5, was 10 meters squared, then the new area, length times width, 10 times 4, is 40 meters squared. Now notice that the dimensions doubled. 2 became 4, 5 became 10, but the area went from 10 to 40. It quadrupled, or it got multiplied by 4. Multiplying by 4. Why did that happen? Well, an area formula with a scale factor can be developed if we just sort of, instead of calling it 2 by 5 or 4 by 10, we're just going to call the original one as a rectangle with width and length of W and L. And then when I scale it up by a factor of k, I multiply those dimensions by k. So the width becomes k times W, and the length becomes k times L. Okay, so the area of the original is L times W. The area of the scaled up diagram, though, is going to be kW times KL. And notice that when we multiply all that together, we still got our length and our width multiplied, but we've got two k's in there. Multiplying those together gives us k squared. So what that tells us is that the area of the image is k squared times the area of the actual, or the original. Or if we divide both sides by the area of the actual there, we get k squared is area of image over area actual. So when we deal with areas, it's not just k anymore, it's k squared. We call it a squared scale factor. Okay. So here's an example. A floor plan is drawn to represent a house that has a total area of 1,000 square feet. So that's the area of the actual there. It's 1,000 square feet. What is the area of the diagram if the scale factor, so k itself, is 1 to 50? So we want the area of the diagram, or the area of the image. Well, we just saw that the area of the image should be equal to k squared times the area of the actual thing. So in this case, that's 1/50th, 1 over 50, squared times 1,000. Okay, so if I have 1 over 50 squared times 1,000, let's square the 50 first. So we got 1,000 divided by 2,500. We can reduce this fraction quickly. A couple of zeros go away, and then 10 over 5, I think, is the same as 2/5. Okay, so 0.4, and that would be in square feet. So we can see that we scaled that down rather substantially from 1,000 square feet to 0.4 square feet. All right, so that's how scale factor works with areas if we want to find the area of the image given the scale factor. Well, what if we want to find the area of the original starting from the image, or starting from the model? So scale model of a ship is built with an area of 120 square centimeters for the ship's deck. Okay, so the area of the image this time is 120 centimeters squared. What's the area of the actual ship's deck? The scale factor, k, is 132, 1 over 32. Okay, I'm going to start with my formula that says k squared equals area of image over area actual. Now I know I've got 1 over 32 that has to be squared for my k here, and the area of the image is 120 centimeters squared, so the area of the actual is the thing that we want to find, a actual. It's hard to think in your brain to write two A's together. It's like Aaron, it's a hard name to write sometimes. Actual. Okay, so let's square the 1 over 32 first to get that out of the way. So what's 32 squared? 32 squared is 1024. So I've got 1 squared over 32 squared gives me this, and that's equal to 120 over the area of the actual, which is the thing that we're looking for. So I just cross multiply. We've seen this strategy before. So I've got the area of the actual is actually going to be ending up being 120. It's dividing by the square of the scale factor, which was 1 over 32, which is multiplying by 32 squared. Okay, so I got 120 times 1024, and that gives me 122,880. All right, so I've got 122,880, and that's going to be in centimeters squared. That's a huge number to represent an area. Let's convert that into meters squared and see what we get. 122,880 centimeters squared. So remember our conversion factor for meters to centimeters looks like this. But if I want to get rid of centimeters squared, I'm going to have to square that scale factor. So the centimeters squared are gone, and I got 122,880 divided by 100 squared. Let's see. I get 12.28, so this is equal to 12.288 square meters, which is a reasonable area for a ship's deck or a boat or whatever it is. All right, so there we go, scaling up and down. When creating scale diagrams of an object, the ratio of the areas results in the square of the scale factor. That's a big thing here. So the area of the diagram is found by multiplying the area of the actual by the square of the scale factor, whereas the area of the object is dividing the area of the scale model or the diagram by the square of the scale factor. Now remember, we multiplied by the square of 32 in that last example, but we were actually dividing by the square of 1 over 32, which is why we ended up multiplying there. So when you're going from model to actual, you're really dividing. Strange. All right, good luck. See you next time.